Hello, Masuma here. Okay, I turn on demonstration. So, I decided to consider graphs and DFS, but we have another topic, DP on masks. In this topic, we must consider many tasks on graphs, and I decided to uh, consider graphs before this topic. So, we already discussed the graphs, but let's uh, discuss it more formally. Um, okay, what is a graph? Undirected graph. Undirected. I Undirected graph. Maybe I turn off this demonstration because I have a lax. Um, you can watch my translation, my what I write in Miro. I have a lax and I turn off the demonstration.
Здравствуйте.
Здравствуйте. Так, okay. Once again, today's topic is graph, and so what's undirected graph? It's a pair when if where the set set of verticals and E is a set of x pairs where x and y is belongs to y. Okay, simple example. If we have some verticals, for example, something like this, then we have verticals v2, v3, v4. This is graph G, and verticals of this graph will be v1, v2, v3, v4, and edges will be pairs. Will be not pairs. In an undirected graph, we have not pairs. We have subsets. We have sets. We have sets, and it will be when one, two, two, v3, and v3, v4, and v4, v1. I take I take set because it's unordered, and for example, in the directed graph, we consider pairs because pair is ordered. Directed graph. What is this? Equals to VE, where V is set of verticals and E is a set of pairs. Set of pairs. Usually directed graph or oriented graph usually it represents like this, arrows and points, and if you have some graph, V1, V2, V3, V4, set will be the same. And edges will be V1, V3, V3, V4, V3, V2 pair, and pair V3, V4, V1, V3, and V3, V2. It's all. Okay. So consider walks in graph. What is walks? Walk V1 and so on, VK. Let's suppose in oriented graph. Is sequence of verticals. Verticals where V1, V2 belongs to E and so on, and Vk minus 1, Vk belongs to edged. Okay, in undirected graph it will be sets, and we have another definition. Open walk. What is open walk? It's a walk V1, so on Vk, where V1 not equal to Vk. For example, if you have some walk in the graph, this and this verticals is not equal, and in cos walk it's the same walk but V1 the key where what where one equal to the key. So for example, this will be this will be the closed loop in graph. So next definition. What is trail? What is trail? Trail is walk. Trail is walk, but edges, but in which no edge repeated. In which no edges repeated. For example, this will be a trail because there's no edge repeated. She's only the vertical, and in this case, no. If we go to this edge double, it will be not trail. So that's definition. Pass. What is pass in graph? Pass is walk, is trail. In which no verticals repeated. Why is it true? Why we consider some this not be pass, and this will be pass, for example. Why we don't consider way walk? Why we don't consider walk with no verticals, but no verticals repeated, but with edge repeated, because if we repeated some edge, it means we repeated verticals too of this edge. Okay. So the next definition, which is next definition. Let's say that vertex is reachable. Where is reachable? From O, if there's a pass from O to where. Why we consider pass, not walk? Because if we have some trail, for example, we can consider only we can consider pass in this trail always. We can find it. So from U to V, when V1, Vk, where V1 equals to U and Vk equals to V. So next definition. What's this connectivity relation? Consider G, indirected graph. Indirected graph. And we consider a connectivity relation. What is connectivity relation? Between O and V. It's denoted like O V tilde V. If there's a walk from U to V, so the statement connectivity relation in undirected graph is equivalence relation. Do you know what is equivalence relation? Hello?
Yes. Yes, yes. I know.
Okay. It's good. So what is reflexivity? How to prove it? So we have V in our graph. We have some V. How to what will be pass V to V? It will be just walk, not pass. Walk will be just V. So flexibility is obvious. Symmetricity. U, V. We consider undirected graph, and we already have if we have walk from U to V, it means we have a walk from V to U. because the graph is undirected. Yeah. Okay, and then transitivity. Transitivity. If we have some path, some walk from A to B and walk from B to C, then we have a walk from A to C. Just we connect two paths and get this walk. Okay. So we consider connectivity relation in an undirected graph, and so the next definition: components in graph are equivalence equivalence class by tilde. What does it mean? If we have some graph, and we have we have some components in this graph, if in these components we have edges that not if we haven't edges that that located through components. Okay or not okay? We just divide our graph through on components, and in this components we haven't edge between them. We in these components will have maximum size, maximum verticals, which every component will be contain maximum of verticals. Okay, yeah, I think I explained what this means. That definition. We consider undirected graph, and let's consider directed graph, oriented graph. Oriented graph G have strong connectivity relation between U and V. It means we denote it like this, and this this strong connectivity relation exists between U and V if there exists exist, uh, there exists a walk from U to V, from U to V and V to U. If we have verticals in our graphs, in our graph, strong connectivity relation exists if we have this edge and this edge. Okay. Wait, I mean this way, not edge. Some way to this, some walk to this, and some walk to this edge, this vertex. So statement statement no new strong connectivity relation is equivalent relation to y, because there's reflexivity, obvious. There's symmetricity because in our definition we have way we have if we have way to some way to from x to y, then we have a way to y from y to x because of our definition and transitivity. We have some ways, some walks, then we have walk A to C to C. So in this graph we consider strong connected. We consider not components. We consider strong connectivity connected components. We consider strong connected components in our graph, in oriented graph. There's strong connected components in oriented graph. Strong connected components in oriented graph are equivalence class by tilde. No, the same, but notice that if we have some graph and if we have strong connected components, if there exists h from U to V, from some U from these components to V from components C2, it doesn't mean that it doesn't mean that it doesn't mean that we have that um, this component uh, must be must be general, must be general, and must be union of C2 and C1. But if there exists another C2 and C1 are union of C2 and C1 will be new component. Okay. So okay, do you have questions about definitions? Секунду. 1 second. I have a messages. Do you have a definition? Do you have questions about definitions? We are done studying DP. No, we haven't done studying DP because because um, I I want to I wanted to consider topic DP on masks, and in this topic um, there are tasks on graphs, and I think you it will be better if I consider um, consider graphs, and then we consider the last topic on the pair. So so you haven't questions or have about definitions? I think it's obvious. And so let's consider how to store graphs in computer memory. Storing graphs in computer memory. We consider um, only adjacent matrix, adjacency matrix. Let me remind you what is adjacency matrix. I think we can make сейчас 40, да? Нет. Okay, consider adjacency matrix. What is it? What is this? Adjacency matrix is matrix M where img equals to 1 if there exists h and all else. In graph G that oriented and not multigraph. The next definition, the next okay, What's the pros and cons of this type of storing? Um, we can simple uh, check if the edge is exist, but uh, the memory will be O1 squared because we have matrix, we have full matrix. So um, we have another methods. These methods have less memory, list of edges. If we have so this list of edges, which is just we just contain we just contain pairs, std pairs in C++ and in vector. And it's a way to how we store a graph too. What is the pluses? What is the pros? Uh, pros is naturalness. Naturalness. Why? Why? Because no, because if we when we input our graph, if it always looks like uh, looks like pair of edges, and we just we just input pairs online. We can input pairs online and fill our graph when we read input. So minuses: inconvenience, inconvenience of processing, inconvenience of processing. Um, no, we have some list of edges and how to find if there exists an edge. Just iterate through this array and find this edge. It will be on, and it's very inconvenient. I don't know where's the list of edge is using, um, but the most but usually you you will we will use adjacency list, adjacency list. Okay, let's have a break for 10 minutes, I think. If you have any questions, you can send questions to the chat. I checked your расписание, and you have only 5 minutes of break. So let's continue. Um, mhm. Adjacency list. What is this? Um, we contain list, the list of um, the list of verticals, and what does this mean? Um, what does this mean? Нет, not list of verticals. We contain pairs, and mm, we can get edge by vertical. We can get verticals that reached from some vertical in list. What I mean, if you have U, some vertical, and you have edges, and V1, V2, V3, V4, we can get this edges um, by um, by U. Can get list of this vertical of these pairs of edges. And usually this list is vector, std vector. And usually we will use this type of storing. So what's the process? Um, required only required only O n plus m memory, because you have graph with no edges. You have graph with you have, for example, this graph with 5 verticals and more edges, and you choose ON or OM. All memory depends on depends on verticals and edges, and we use plus. So and minuses. So ну как бы we can check if there exists edge for O1, because if the grass will be like this, look like this, we check every of edge, and This will be on. And but it can be fixed by hashing, and I tell you a little bit later about this. And so it's not minus, and it's just uh, neutralization. In neutralization we can't check h1. And another plus for every vertical, we know vertical vertex, we know it neighbors. We know it neighbors. If we consider some vertical, we know that uh, we can get list of the edges of its edge. Yes. Um, so, do you have any questions about storing graphs? No, it's obvious, I think. So the next will be DFS. DFS. We considered DFS in the previous semester, but it was on trees. It was on trees, and it will be just it will be traversal. DFS on trees it equal problem. Just DFS on trees equivalent to traversals. You wrote traversals before, and we in this part we consider graphs. We consider not trees. So let me put presentation to mirror desk. Not presentation, visualization, what's the DFS, what is another methods. Сейчас. Do you see the video? Do you see the video on mirror desk? Suppose you see. Um, Consider only DFS and BFS. In DFS mm, we mm, we continue to go. Uh, we continue to go. Yes. While we don't reach the last vertical. In BFS we traverse through all the verticals. Just it will be better if I start to draw. In DFS you will traverse our graph like this. We reach end, and when we reach end we return and continue. So it looks like this. In DFS we traverse like this. We traverse first layer, then second layer, okay, and so on. Сейчас, ну тут, наверное, не будет. Okay, let it put here and formalize DFS. Блин. Так. So, вот the pseudocode. Ой, vector. We need vector for we need vector of vectors to store our graph. Vector of vectors of int to store our graph G. In this way, verticals will be int integer. We store another vector with integers, tint out, and we store color. I'll explain later. I will explain later what does this mean. We store vector color ой, color char color so we will have only three colors: white, gray, and black. And when we vertex is white if it's not visited yet. Gray vertex is gray if it visiting now, and black and vertex will be black if it was visited. Okay, so like in this visualization, we have white verticals and blue verticals that is already visited. So we have vector int parent to store parent of verticals. And so let me write algorithm DFS. DFS will be um, consists to contain two arguments, int p equal to -1, and when we visit our when we just start to visit our vertical, we create timer. We store time for this vertical. Parent of this vertical will be pair. And color, as we start to visit this vertical, it will be gray. Сначала all the verticals are white. And then we color it by gray and black. So the next will be we want to iterate through all the parents, or all the точнее, just we want to iterate through all the sons of this vector, all the edges that verticals that reaches from this edge, from this vertical. And if color is white, then we continue. It's not white, then we continue. It means that we for example, let it be white, let it be gray vertical, white vertical, yeah, gray, and we go through our array and meet gray vertical. It means we located in recursion, and it means we find a cycle, and we just continue. И пропускаем this vertical. So we call recursion for all sons, and then we just say that we went out from our vertical and color of this vertical will be black. There's the algorithm. Do you have any questions about algorithm? T out and T in arrays will be needed in proofs that DFS works. Mm-hmm. Okay. The next is lemma. To to prove that all the verticals that reached from vertex S are visited in DFS algorithm, we need to um, prove it by the next lemma about white paths. If at the moment team v exists exists some path from v to u, that is white vertex to white vertex. Um, then at the moment T out v all the verticals in pass will be black. If you have some pass, and we start to DFS from this vertical. This vertical will be white, and after start, this vertical will be gray. This means all the verticals after when this vertical uh, will be black, these verticals will be black too. So this что ж, consider once again this v and pass and some verticals set this color to black, and there exists a vertical that after um, set, this vertical is not black, and we consider two cases. Which cases? Uh, this vertical is white. Some vertical in our path is white. It already contradiction, because if you have some vertical, if you have edge PU, we consider some vertical U, and you consider parent, or you consider its parent P and rebro and edge PU. And edge PU was considered in DFS because because uh, because this vertex P is black. That means you consider all the edge um, that located from P. Do you understand? Okay. So the next case, use gray. What does this mean? Так, ну, это тоже it's two contradiction. Why? Because if you have because if you have we visited where, then we visited you, then we visited you, and it's but in our case we went out in Oftial from where, and then we went out from you. That's not true. That's contradiction, because if you have recursion, you 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 just if you have a recursion, we must to get out from this uh, from outer recursion. So from inner recursion, from for get out for outer recursion, from outer recursion. Okay, not okay. So consequence consequences, some consequences uh, from this name. If we launch DFS from S, then after processing DFS visited only verticals, only verticals that were reachable from S. Okay, that's obvious, I think. The next consequence, if you carefully look to this lemma, it's the same that, but in other words. Consequence, another consequence. Let in main the FS is performed. The FS is performed. Then if there's exists a cycle that is reachable, that is reachable um, if there is a cycle that is reachable from us, from our start vertical, that's equivalent to what? Hmm? Explain this the first found edge to the gray vertical. So why is it true? Let's prove it. We have okay, the first found edge to the gray vertical. So every time the recursion stack. Is walk. Сейчас the recursion stack is walked. Is walked. Yeah, is walk. Of gray verticals. And all the gray verticals located are located where? Located in the recursion stack. What does this mean? Okay, when we go down through our recursion, we all the verticals are gray, and all the gray verticals located in recursion stack. So what happened? What happened next? If we consider some verticals as the to u, we found a cycle because um, because because when we found gray edge that is exist from to gray vertical, there will be cycle because all the verticals are gray. That means they not visited yet. Okay, let's do. We have some cycle. We have some cycle S. So we consider vertical V. We consider vertical S, and this vertical, of course, have minimum a minimum 10, and then we use lemma about what, about white pass, and all the verticals of the verticals in this cycle will be visited. We use this lemma. In particular, where this vertex v, and the edge will be u. And the edge is previous u. And the edge will be u. Do you have questions? DFS, it's necessary to prove that DFS works correctly, and we just prove by these lamps and these statements that it works. So we have all n plus m complexity of DFS y. Ну, я уже объяснял. I already discussed that. И last node. To find cycle, you need to use parent. You need to use parent. How? You just you consider sequence and consider vertical web, and you found edge. You found edge to the gray vertical too, and how to find cycle, how to print cycle. We keep all our verticals in this array, in parent array. We store all the parents in this array, all the parents of verticals in this array. And to find parent of vertical web, we just call vector parent web, and to find parent of this vertical, we just call parent of parent web, and so on. We continue while we don't meet 2. Okay? But while parent from u not equal to 2. Okay, so that's all. I think if you have any questions. Well, thank you for seminar, for lecture. See you later.
У меня есть вопрос. Ну,
Давайте.
я просто хотел уточнить в конце, Просто
Мгм.
вдруг, если у ребят по теме, у меня просто не по теме.
Не по теме. Что? Что? Я не понял.
Да, у меня, по
А, не по
теме
теме вопрос?
совсем.
Хорошо, давай. Задавай.
А вот можете подсказать какую-нибудь книгу на русском? Вот потому что мы сейчас проходим.
Ну хорошо, ну что, могу кинуть конспекты наши, там, могу кинуть...
Не, то, что вы скидывали видосы, это окей. А может быть, есть какая-нибудь книга?
Не, я понимаю, да, ну, Кормана книга есть. Сейчас, ну, я могу скинуть, в принципе, тебе в личку конспекты фифта, вот, и там это все есть.
Ну, я буду благодарен. Спасибо.
Все, давайте, goodbye.
До свидания.
Мгм.